Okay, so having reviewed the equation for simple harmonic motion that was originally developed in Physics 1, originally solved in Physics 1, we're going to take an extra step. And the first step we're going to take is to include what's called damping, which is really just dissipation or friction. Now, for simplicity, we're going to take drag to be linear. That means it depends on the speed and not on the square of the speed. So we have linear drag. Remember that velocity is the derivative of position, and that that can be written as x dot. And the minus sign is really just direction. It says that, as a vector, the force is opposite to the direction of the velocity. So in scalar terms, anyway, if we assume that we're moving to the right and our position's positive to the right of 0, then you've got a kx force to the left, and you've got a cx dot force to the left. So if we apply Newton's second law, it's kx in the negative direction and cv in the negative direction that equal ma. But of course, acceleration is the second derivative of position. So we can write it like that. And then we can gather all the terms on one side. So mx double dot plus cx dot minus, or plus kx equals 0. Okay, so now we're going to do some algebra on that. First thing we're going to do is we'll divide by m. And that's going to give us x double dot plus c over m x dot plus k over mx equals 0. We'll introduce the natural frequency of the spring, root k over m, and that means this is omega naught squared. This will stay the way it was, x double dot. And then we'll introduce this constant gamma, c over 2m. So we see what we really have here is we have 2 gamma. So this is a second order differential equation. And we saw that without the damping term, the solution was sines and cosines. We saw last time as well that sines and cosines are really complex exponentials. And so what we're going to do here is just try an exponential function in there. And alpha is going to end up being a complex number. So if this is x, then x dot, remember that's the time derivative of x. So that's the time derivative of a e to the alpha t. So we know how to do this from Cal 1. The a is a constant. It comes out. The derivative of the exponential function is itself times the derivative of the exponent. Well, the time derivative of alpha t is just alpha. Now, if we do the second derivative, then we're going to get alpha once, alpha twice. We're going to get a term that looks like alpha squared. So when we put all those in, well, I guess we'll do it once. A e to the alpha t alpha squared, that's this one. Then we're going to have 2 gamma times this, a e to the alpha t times alpha. Then we're going to have omega naught squared times x, that's a e to the alpha t. And all of that's got to be 0. So we see there that a e to the alpha t is a common factor, so I can factor it out, and it'll never be 0, so I can divide by it. And I'm left with an equation that must be true in order for this to be a solution. So it's a relationship that was going to tell us something about what alpha is. Because a is going to be set by the initial condition. It's alpha that we want to figure out. So this is called the characteristic equation. And it's a familiar quadratic. So a is 1 here, and then c is omega naught squared. And then we divide by 2 times 1, which is just 2. And then both these have 4 in it, so you factor out root 4, which is 2. And then you can distribute the division, divide this by 2 and this by 2. With the result, you get minus gamma plus or minus the root of gamma squared minus omega naught squared. So our equation then, a e to the alpha t, if we put in this value of alpha, we get minus gamma plus or minus this radical times t, and that is a solution of the differential equation. Well, let's investigate that a little further. There's three cases we're going to consider, because you notice that we have a square root there that's gamma squared minus omega naught squared. So first of all, if that's positive, now remember gamma was c over 2m, and c was the drag constant. So this is going to be the case when you have a big drag constant. So lots of drag. And it's sometimes called over-damped. Means there's way too much damping here. And damping is just another word that means friction. So if that's the case, then if you look at the exponent we had negative gamma plus or minus that radical. Well, if gamma squared is really big, then this is just going to be a real number, because it'll be positive, and then you could do the root. But of course, because gamma has to be bigger than gamma squared minus omega naught squared, because subtracting omega naught squared makes it smaller inside, gamma's got to be bigger. So if you do minus gamma plus this root, the point is that you end up with a negative real number, okay? You end up with exponential decay. Because this negative number is bigger than this positive number. And that means that for your position, it just does something like this. It just goes to 0 pretty quickly, okay? So, and that makes sense, because if you have lots and lots and lots of damping, then even if the mass is on a spring with a huge amount of friction, you're going to pull it over and let it go, and it's just going to stop. The spring might pull it a little bit at the beginning, but it's just going to stop almost right away. So that's our first case to consider, lots of drag. The second thing that could happen, and this is kind of, you may remember like in Math 11, when you solve quadratics and you start to look at the three cases, you can have two real solutions. The next thing that can happen is that square root can disappear, in which case you get one real solution from your discriminant. This is really the discriminant function from Math 11 and 10. If that's 0, then then the radical just disappears. And then these two things are the same, right? A e to the minus gamma t and b e to the minus gamma t. Well, it turns out, because we still need two independent solutions, that the second one is something like the order bt. But the point is, it's still exponential decay, okay? This time means you might get some, you might get a little bit of oscillation, but eventually it'll just drop out to 0 really quickly. Okay, and that might be called something like critically damped, but it's not very interesting to us. The most interesting case is the small damping case, small friction. So that means that gamma is small, and that means when you subtract omega naught squared, you're getting a negative number. And so then our exponential, which had something like gamma squared minus omega naught squared, and that's going to be a negative number under the root. So this is negative. And we know that the root of a negative number is complex. So the way that we represent that explicitly is, first of all, we factor out a negative. And now what we're left with here is a positive number. So we pull out that -1 explicitly, and then we're left with something here, omega naught squared minus gamma squared, that is explicitly positive now. And therefore, the square root is real. Now, the square root of -1 is the complex number I. So this is I times a real number. And so we put that in for our alpha constant in the exponent. Now, the reason this is interesting is that we get sort of two parts to this function that are multiplied together. We have a real part, which is exponential decay, and that comes from this part of the alpha. And then we have a vibration, which comes from this. That's the complex part. So if we split that up a little bit, we could use the law of exponents, right? This is a e to the minus gamma t, and then a e to the plus or minus I times that radical, omega naught squared minus gamma squared, t. So this part here, I could use color here, that would be nice. So we've got the exponential decay part. So I'll underline that in red, exponential decay. That's this term here. And then we have a vibration. Now, the vibration, it doesn't look like a vibration to you yet, but e to the I omega t we saw last class is like cosine omega t and sine omega t. So this is kind of go up and down and up and down and back and forth and back and forth and back and forth. And then this term out in front, this is sort of like the amplitude getting smaller and smaller and smaller. So this would be a vibration, and this is an amplitude that decreases with time. Now we see that there's really two answers here, and we know we need those two answers. So the conventional way to write that is not with 1a, but with two different constants, c1 and c2. Here is the e to the positive I square root t, and then here's e to the minus square root t. Now, what is that square root? Well, it's a square root of an omega squared that gets a little smaller. So we're actually going to call it another omega. We're going to call it omega, I better write this really small. We're going to call it not omega naught, which is the natural frequency. We're going to call it omega d. And the little subscript of d is just going to reflect the fact that we've got damping going on now. And so the frequency of the oscillating part is actually a little bit smaller than if there wasn't any friction present. So here we go. So the EI to the omega damping t. Whoops, that t came out of the exponent. It should stay inside the exponent. And now I've got to make it all small again. Oh my goodness. By de Moivre's theorem, that's like cos omega damped time plus I sine omega damped time. And so this new function that we don't have a lot of familiarity with, we see that it is related to a vibration. Now, here's that variable that we introduced, that omega damped, right? This is the new angular frequency of the vibration. It's made a little bit smaller by the presence of friction. This gamma constant, remember, is related to the drag constant, so it reflects the amount of friction that we have. So that's one way to write it, as a sum of complex exponentials. The other way to write it, or the other ways to write it, we can appeal to what we did last time. We can write it as a sum of cosines and sines, again with that exponential decay term in the front. Or we can rotate the cosine function in function space and introduce just an initial phase. And this just enables us to match up any initial conditions. So something like this. So that position is a function of time. Now here, again, we can see this is like an exponential decay in the amplitude times a vibration. So this is just a standard vibration. That's what the equation for sort of standard harmonic motion would be. But now our amplitude is decaying. So the amplitude features exponential decay. And we'll graph this in a minute so that we'll see that that's really the case. Now while we're here, though, if this is the position, velocity will be the derivative of that. And you can see we're going to have to use the product rule. So we'll leave the first term fixed, and then we'll differentiate the second one. So we'll get a negative out of that, and it'll be sine omega damped t plus delta. Then you got to do the derivative of the inside, so times omega damped. And then we've got the other term, of course, plus a, and then we have to differentiate this one. That'll be itself times minus gamma, I'll put that at the end, times cosine omega damped t plus delta. So you could see that that problem that we did last time of matching the initial conditions is going to get a little bit more complicated because now there's two velocity terms. Okay, but we'll leave that for now, and I guess our first example we'll do is a little bit simpler. So here we've got a mass on a spring. So it's, you know, it's your standard physics problem here. Mass on a spring, and we know the K constant, we know the mass, and we know the damping constant C. So remember, the two forces are a kx in the negative direction and a c times the velocity opposite to the direction it's moving. And for simplicity, we said it's moving to the right and the position's positive. And then that equaled ma. And that led us through to that solution, the equation that we got for position as a function of time. Okay, so just to start to understand what these terms mean, a very simple example. First, let's find the gamma constant. That was defined as c over 2m. Ooh, what happened there? C over 2m. And that emerged, remember, when we took this equation and we first divided through by mass, and then we made a couple of substitutions. The first was we let gamma be c over 2m, and then that made this into 2 gamma. X double dot. Okay, so what is it? So this is 18 units, I didn't specify the units of c for simplicity, over twice the mass. The mass is in kilograms. And that's 18 over 6, that's 3 units. Now what should the units be? Well, we also substituted in omega naught squared here. Then we tried a function that looked like a e to the alpha t. We got a quadratic for alpha when we differentiated twice. And I know I'm going through this a couple of times, but it's something eventually you'll want to be able to do this derivation, so it's worth repeating. And then for the alpha constant, we got minus gamma plus or minus gamma squared minus omega naught squared. Now, in order to know what sort of case we have, we better find omega naught, right? So it's the root of k over m. K is 75, the mass is 3. So that's root 25, that's 5 rads per second. So clearly omega naught's bigger than gamma. So we're in that case of small friction. And you remember we factored out an I, we took the square root of -1 and made it I. Then we switched that around as a result of the factoring out the -1. And now we have the square root of a real number here. So this is a real number multiplied by I. Okay, now clearly, if we're going to be doing omega naught squared minus gamma squared, this better work out to be rads per second, and you can check that on your own. We want to know what omega damped is. That's the angular frequency of the vibration when there's friction. It's given by this expression here. So that's 5 squared minus 3 squared. That's 25 minus 9. It's root 16. It's 4 radians per second. So the rate of vibration has slowed down a little bit because of the friction. The period, well, period is still going to be 2 pi over omega, but in this case it'll be over omega damped. So that's 2 pi over 4. That's a half pi, so what is that? 1.57 seconds for the vibration. Okay, so we had tried this solution, and so we know that our solution x can be written in several forms. We can write it as like C1 e to the minus gamma t e to the plus I omega damped t plus C2 e to the minus gamma t e to the minus I omega damped t. Or we can write it as a e to the minus gamma t cosine omega damped t plus delta. Sorry to squeeze you in there. And there's one other form where you write it as, what did I say, a1 times this decaying exponential times cosine omega damped t plus a2 e to the minus gamma t times sine omega damped t. Sorry for the repetition, but we could pick any of these three to describe the motion. I'm going to pick this one just because it's easiest. And now, so we know omega damped, we know gamma, so we know our solution sort of looks something like this. Position is a e to the minus 3t cosine 4t plus delta. And we want to use the initial condition to find the values of a and delta. So we're told the mass is at rest at 0.75 and at time 0. Okay, so at time 0, so we put in time 0 there, and then that's just going to be cosine delta. And that's time 0, so that's just 1. And so this is A, and then the mass was given as 0.75. Okay, so that's the condition for the position. We're also going to need to use the condition for the velocity. And so this simple little problem has become a multi-headed monster, because look at our velocity function over here. So this is the velocity function. And so we can just copy that and then paste it back in over here at the bottom of our solution. And we have to try and figure out now, using this, because this is the initial velocity, we have to figure out what the value of A and delta are. I'll just pause it for a second, do a bit of work cleaning. Okay, so that was our velocity function. So we're going to put in time 0 and velocity 0, and what we know about the other variables. So time 0, that's just 1, that's just 1. A is unknown. Time 0, that disappears, so that's just sine delta. And omega damped is 4. So that's that first term there. That's the velocity being 0. This is A, this is 1, this is 0, because time is 0, so that's cos delta, and then gamma's 3. So we end up with this equation here. So we will take this over to the other side. For A sine delta is minus 3A cos delta. And then we can cancel A off on both sides, as it appears both. And we're getting an equation that we can solve for the tangent. Sine over cosine is tangent, so we just divide through both sides by cosine. It's minus 3/4. So that's going to give us a solution for delta. Now, tangent is negative in quadrants 2 and 4, so we'll have to pick the right one that we need. And then once we've got delta, then we can pop it back in up here, and we can work out the value for the amplitude. Okay, so when we solve that equation, we get a reference angle of 0.69 rads. And so this is 0.69 less than pi, so 2.49. And this is 0.69 less 2 pi. So what was that? That's 5.64 rads. Now, which of those is going to be the correct one? Well, we know that the position's positive, and that's a cosine. So we're going to pick the quadrant 4 solution, because that's going to give us a positive cosine. If we have a quadrant 4 solution here, does that give us the correct initial velocity? Yes, it will, because this will be a negative number. So this side works. And then quadrant 4, cosine will be positive multiplied by negative. That will agree. So we will reject this one, because it doesn't give us the correct initial position. And we'll use this one. So now we can find the amplitude. It is simply 0.75 over cos of delta. So we'll do the cosine of that. We'll reciprocate, and then we'll multiply by 0.75. And then we get 0.94. 0.9374. So our position as a function of time is 0.937 e to the minus 3t cosine 4t plus 5.64 rads. So the initial part of the problem was pretty straightforward, finding the values of gamma, omega, and period. But then at the end, to figure out what the amplitude was certainly a little bit involved.